Welcome to Beyond the Brackets. In this video, we'll learn about binomial distribution. Binomial distribution is a discrete probability distribution used to model the number of successes in a fixed number of independent trials. It is applicable when there are fixed number of trials. Each trial has only two outcomes. Probability of success remains constant in every trial, and all trials are independent of each other. For example, consider tossing a coin multiple times. Suppose a coin is tossed 10 times or 100 times. That means there are fixed number of trials. So the first condition is satisfied. Each trial has two possible outcomes, heads or tails. If getting head is considered as a success, then probability of success remains constant in every trial, that is 0.5. Also, each toss is independent of the other, meaning the outcome of one toss does not affect the outcome of another toss. As a second example, consider number of students passing an exam. Suppose the experiment is conducted on 100 students or 1000 students here. So the number of students is fixed. So there is a fixed number of trials. Each trial has only two possible outcomes. So either the student passes or the student fails. If passing is considered as success, then the probability of success remains the same for every student. Also, the result of one student does not affect the result of another students. So the trials are considered independent. Other example may be number of defective items in a sample. Suppose we are considering a sample of 500 items. So there is fixed number of trials since the sample size 500 is fixed. Each trial has two possible outcomes. Either the item is defective or the item is non-defective. If getting a defective item is considered as success, then the probability of getting success remains constant for every trial. Also, the outcome of one item does not affect the outcome of another item. So, all trials are independent of each other. Probability mass function of the binomial distribution gives the probability of getting r successes in n trials. It is given by P of r is equal to NCr p power r q power n minus r, where n is the total number of trials, r is the number of successes, p is the probability of success in a single trial, and q is the probability of failure in the single trial. In binomial distribution, there are only two possible outcomes, success and failure, and the sum of probabilities is equal to 1. So we have p plus q is equal to 1, where p is the probability of success and q is the probability of failure. Let's understand the probability mass function of the binomial distribution using an example. Suppose a coin is tossed 10 times and we want to find the probability of getting exactly 4 heads. Let getting a head be considered as a success. Here, total number of trials n is equal to 10. R, that is total number of successes, will be 4. Probability of getting in a single trial P will be equal to 0.5, that is getting head, and probability of failure in a single trial, that is getting a tail, is Q, that is 0.5. Observe that P plus Q should be equal to 1. Probability mass function is given by P of R is equal to NCr p power r q power n minus r. Substituting the values, R is equal to 4, N is equal to 10, P and Q are equal to 0.5. On simplification, we get P of R is equal to 0.205. Therefore, the probability of getting exactly 4 heads in 10 tosses is approximately equal to 0.205. In probability mass function of the binomial distribution, NCR represents the number of ways of arranging R successes among n trials. P power R represents probability of getting R successes, and Q power n minus R represents probability of getting remaining n minus R failures. Now let's understand the binomial expansion involved in binomial distribution. Q plus P power n represents all possible outcomes of n independent trials, where P represents the probability of success and Q represents the probability of failure. Expanding this, suppose in the first case there are 0 successes, that means R is equal to 0. Using the probability mass function, we get NC0 P power 0 Q power n minus 0. For the second case, suppose there is exactly 1 success, that means R is equal to 1. The probability mass function, we get NC1 P power 1 Q power n minus 1. Similarly, if there are exactly 2 successes, so we get R is equal to 2. So this becomes NC2 P power 2 Q power n minus 2. Similarly, for 3 successes, we get R is equal to 3 and it is NC3 P power 3 Q power n minus 3. Finally, since we started from 0 successes, the last case will be n number of successes. So we get r is equal to n. The probability mass function will be NCn p power n q power n minus n. Simplifying this, NC0 is 1, p power 0 is 1, and q power n minus n will be q power 0, that will be 1. Considering all possible numbers of successes from 0 to n, the binomial expansion can be written as summation r is from 0 to n, NCr p power r q power n minus r. Let's proceed to find the constants of binomial distribution. First will be mean of binomial distribution. We know that binomial distribution is a discrete probability distribution. For a discrete probability distribution, mean is given by summation r is from 0 to n r into p of r. Expanding the summation, for r is equal to 0, we get 0. For r is equal to 1, we get 1 into p of 1. For r is equal to 2, we get 2 into p of 2. For r is equal to 3, we get 3 into p of 3. And for r is equal to n, it will be n into p of n. Substituting the probability mass function, we have p of 1 as nc1 p power 1 q power n minus 1. 2 into p of 2 will be nc2 p power 2 q power n minus 2. Plus 3 into p of 3 will be nc3 p power 3 q power n minus 3. The last term will be n into p of n will be ncn p power n q power n minus n. Expanding this using the identity, NC1 will have one term n in the numerator divided by 1 factorial. NC2 will have two consecutive terms n into n minus 1 in the numerator divided by 2 factorial. NC3 will have three consecutive terms in the numerator n minus 1, n minus 2 divided by 3 factorial. For the last term, NCn is 1 and q power n minus n is q power 0, that is 1. So the last term is n into p power n. Simplifying this, we get np into q power n minus 1 plus n into n minus 1 p square into q power n minus 2 plus n minus 1 n minus 2 divided by 2 p square into q power n minus 2, and the last term is n into p power n. We observe that n and p are common in all the terms, so we are left with q power n minus 1 plus n minus 1 p q power n minus 2, n minus 1 n minus 2 by 2 p into q power n minus 2, and the last term is p power n minus 1. The expression obtained is similar to the binomial expansion q plus p power n minus 1 because its terms follow the standard binomial pattern. Since p plus q is 1, so this will be simplified to np. Let's proceed to find the variance of the binomial distribution. We know that for a discrete probability distribution, variance is given by sigma square is equal to summation r is from 0 to n r square p of r minus mu square, where p of r is the probability mass function and mu is the mean of the distribution, which is np for binomial distribution. To proceed further with the expansion, we subtract and add r inside the summation term. Simplifying both the terms separately, for the first term we have r common, so we get r into r minus 1 into p of r, and for the second term we have r into p of r minus mu square will be written as it is. Expanding the summation, for r is equal to 0 we have 0, for r is equal to 1 again we have 0, for r is equal to 2 we get 2 into 1 into p of 2, for r is equal to 3 we get 3 into 2 into p of 3, and for r is equal to n we get n into n minus 1 into p of n. This term is nothing but the mean, which is given by mu, minus mu square will be written as it is. Simplifying this further, for the first term we get 2 into 1 is 2, p of 2 will be nc2 p power 2 q power n minus 2. For the second term, 3 into 2 will be 6, p of 3 will be nc3 p power 3 q power n minus 3. Last term will be n into n minus 1, p of n will be ncn p power n q power n minus n. Simplifying this using the identity, nc2 can be written as product of two consecutive terms in the numerator n into n minus 1 divided by 2 factorial. nc3 can be written as product of three consecutive terms in the numerator n into n minus 1 into n minus 2 divided by 3 factorial. For the last term, we know that ncn is 1 plus mu minus mu square will be written as it is. In all the terms, it is observed that n into n minus 1 into p square is common. In the first term, 2 in the numerator and in the denominator cancel out, and we are left with q power n minus 2. For the second term, 6 in the numerator and in the denominator cancel out, and we are left with n minus 2 into p into q power n minus 3. For the last term, we are left with p power n minus 2 plus mu minus mu square will be written as it is. This expression is similar to binomial expansion because its terms follow the standard binomial pattern. So we get n into n minus 1 into p square into q plus p power n minus 2 plus mu minus mu square. Simplifying this by multiplying these terms, we get n square p square minus np square. We know that p plus q is 1, so this term simplifies to 1, and the value of mu is np minus mu square will be n square p square. These two terms get cancelled. For the rest of the terms, np is common, so we get np into 1 minus p. Since p plus q is 1, so 1 minus p will be q. So variance of binomial distribution is npq. Let's proceed to find the moment generating function of the binomial distribution. The moment generating function is defined as this expression. For a discrete random variable, expectation is given by summation over all possible values. Therefore, this will be equal to summation r is from 0 to n e power tr into p of r. Substituting the probability mass function, we get summation r is from 0 to n e power tr ncr p power r q power n minus r. Combining e power tr and p power r, we get summation r is from 0 to n ncr p into e power t whole power r q power n minus r. This expression is similar to binomial expansion where p is replaced by p into e power t and q remains the same. Hence, the moment generating function of binomial distribution is q plus p e power t whole power n.